Hi, this lesson is all about how the moon's surface evolved over time. Last lesson, we looked at some of the main features of the lunar surface, um, identifying the terrae and the mare, um, and looking at some of the differences between them. What I want to do in this lesson is focus on a small part of the moon's surface, highlighted here on the photograph, in and around the crater that we call Copernicus. You have an image of this part of the moon's surface in page 11 of your Theme 2 booklet. And it's on this page that this lesson is based. What I'd like you to do first of all is to identify any of the features you can recognise that are shown on the photograph. Think about what we've already looked at in the previous lesson. Label them up on your photograph. Maybe press pause now and then watch the video on the evolution of the moon that follows this.
From year to year, the moon never seems to change. Craters and other formations appear to be permanent now, but the moon didn't always look like this. Thanks to NASA's Lunar Reconnaissance Orbiter, we now have a better look at some of the moon's history. The moon likely started its life as a giant ball of magma formed from the remains of an impact on Earth about 4.5 billion years ago. After the hot material collected into a sphere, the magma began to cool, eventually forming a crust on the surface of the moon with the magma just underneath. Around 4.3 billion years ago, a giant impact battered the moon's south pole, forming the South Pole Aitken Basin and sending debris as far as the opposite side of the moon. This impact marked the beginning of a period that would cause large-scale changes to the moon's surface. One by one, more huge collisions shaped the terrain, some forming large basins that would eventually fill in to become the dark-colored patches of the moon, known as maria. They began as normal craters, but soon started to change due to the size of the impact on the relatively thin crust. Because the moon had not yet fully cooled on the inside, lava began to seep out through the cracks caused by the impacts. The resulting volcanic activity spread lava throughout the craters, gradually filling them in and cooling. Because of the high iron content of the basalt in the rock, the maria reflect less light and therefore appear darker than the surrounding highlands of the moon. Around 1 billion years ago, volcanic activity ended on the near side of the moon as the last of the large impacts made their mark on the surface. The moon continued to be battered by other impactors, although they were much smaller than the objects that formed the largest basins. Some of the largest, most recent, and best-known impacts from this period include the Tycho, Copernicus, and Aristarchus craters, which are unique due to the complex system of rays that stretch out from the impact site. Finally, we arrive at the moon that we see today. Though the surface continues to be affected by impacts, the rate has slowed down drastically to the point where the moon appears unchanging to the human eye, as a permanent record of its own history, and a glimpse of how craters may have formed here on Earth.
When we look at this photograph, it's perhaps a good idea to get some idea of scale as well. If you look at Copernicus, the main crater in the middle of this image, it has a radius of 93 kilometres, so that's 186 kilometres across. That means that you could comfortably fit Wales into that crater. Not only that, it has a depth of 3.76 kilometres. So we could stack up 3.5 Mount Snowdons on top of each other and it still wouldn't quite reach the rim. Now, craters like Copernicus go through a series of stages of formation. Watch this video and we'll come back to the image in a moment.
Hi, we're here today with a fun and educational activity that you can do at home, at school, or even at a camp. And it involves making craters. Go outside tonight, take a look at the moon, and you'll see these circular features with lines coming out. Those circular features are craters, and the lines coming out are ejecta patterns, rays. The way those craters were formed were from rocks coming from outer space and smashing in to the surface of the moon, pulverizing the soil there, what we call regolith, and spraying it out along those ejecta pattern rays. You can make your very own craters. You start with about an inch of some flour, spread out nice and smooth, and then take something that is of color, like these are little cake sprinkles, and kind of just sprinkle them evenly over the surface. Then you need another layer, and what we've selected is cocoa. You can sprinkle it with your spoon or sift it over the top, which will make a more even surface. To simulate a rock impacting a surface, drop them from a reasonable height. I'm going to use this big rock first. As you can see, this impactor made a very nice crater. This indentation is the crater. The impactor, the rock, is outside because it actually bounced out. That happens sometimes in real life. And you see that it threw out a bunch of the subsurface material. And we have our own little geologic excavation. The white things coming out, those are the rays, just like you see on the moon. And some of our sprinkles got thrown up, and that represents the mineral diversity of the surface that was impacted. Not all meteorites come in perpendicularly. Sometimes they come in at an angle. Take it and kind of chuck it at an angle. You see that the ejecta pattern is a little bit different. Notice there are no ejecta rays on this side, they're all on that side. From looking at a crater, something we can tell is what sort of angle the impactor came in at.
Okay, now we've watched that video, pause this image and see if we can label up any of the features of the craters that are mentioned in the video and on these diagrams, and annotate your image of Copernicus and some of the other craters to show what these are. Okay, let's try and put all this together. If we look at the image of this part of the lunar surface, there are 5 different key features on here. They're listed as part of question E on page 11. What I'd like you to do is to see if you can work out some of the geology of the moon. What order did these 5 different events occur in? Can we list them on the table with the oldest one at the bottom and the youngest one at the top? And give reasons for why you think these events occurred in this order. Press pause now, see if you can work it out. Okay, now we're back, let's have a look at some of these answers. So this is the image with some of the main features labelled up. The mare there on the top of the image, to the north, the smoother area. The rougher, more heavily marked with meteorite impacts, the terrae more towards the bottom of the image. The order of formation is this. The Montes Highlands, the terrae, must be the oldest thing. Everything else either impacts or cuts into that. Secondly, we have Eratosthenes. This crater clearly impacted into the into the terrae, but any rays from Eratosthenes, and it is quite a big crater, have been covered up. They're not apparent. The Imbrium Mare, then, the flat area to the north, must be next. It clearly is filling up a hole in the highlands, but we can see that the rays from Copernicus are on the top surface of that mare. So Copernicus must have happened after the mare was erupted. And finally then we can see the whole area, including the smooth surface of the mare, pockmarked with these small meteorite impacts. So, to conclude, we can see, just by some careful observation of parts of the moon's surface, how this surface must have formed. And we can even start to piece together the sequence of events that created our moon. Next time we'll try and apply some of these ideas to a different planet.